Here is our second example of graphing a rational function. We're going to graph f of x equals 2x plus 1 over x minus 1. So this is a little bit more complicated than our first example. And we are also going to just sort of plot points. We're going to kind of explore and plot a lot of points, find our way through this. It's only after this example that I want to develop the step-by-step process that we're going to use, because I think we need to see one more example in detail before we start jumping to conclusions about where asymptotes are located and such. So let's go ahead and get started with just right now we're just going to try to plot a bunch of points and figure out what this graph looks like. And I have another sheet of paper where I'm going to be doing some calculations. So this is the function we're looking at. And one thing I didn't say in our previous example is just like graphing we did earlier in this course, it's always kind of easy to look for a y-intercept and x-intercept. So first let's look for a y-intercept here. If we set x equal to 0, f of 0 for this function is 2 times 0 plus 1 over 0 minus 1. That's 1 over minus 1, or negative 1. So the y-intercept is the point 0, negative 1. I actually have 0 on my table here on this side. I'm just going to fill that in. We can also see if there's an x-intercept by setting y equal to 0, or setting the function equal to 0. We're going to set 0 equal to the function expression, 2x plus 1 over x minus 1. And what I can do here is I can, to solve for x, I'm going to multiply both sides by the denominator. So I'm going to multiply x minus 1 times 0 equals, take that 2x plus 1 over x minus 1. I'm also going to multiply that by x minus 1. I can write that over 1, and that makes it easier for me to see that the x minus 1 is going to cancel on the right, so I have 2x plus 1 on the right. On the left, anything times 0 is 0. So I have just 0 equals 2x plus 1. And notice that this is just the numerator of the fraction. And we're going to see this pattern over and over again, that when we're trying to find the x-intercept or intercepts, we'll just be setting the numerator of the rational function equal to 0. A fraction can only equal 0 when the numerator is equal to 0. So we still got to solve for x here. I got negative 1 equals 2x. So negative a half equals x. That means negative a half, 0 is a point on our graph. And I might just, I don't have a space for that here in my table. I add negative 1/2, 0 as another point on my table of values. So we can go ahead and plot those. I mean, we have 0, negative 1 on my graph, and we have negative a half, 0, so that's right here. Notice I'm making each unit is 2 squares, so I'm spreading out a little bit on the scale for this one. Now, of course, we need some other points here to plot, so the x-intercept and y-intercept tell us a little bit, but not too much. So I'm going to go ahead and just plug in some values, negative 3, 2, 1, 0, 1, 2, 3, and see if we can get some more points to plot. Now when I plug in negative 3 into this function, 2 times negative 3 is negative 6, plus 1 is negative 5, over negative 3 minus 1 is negative 4, right? So notice I get a negative over a negative is positive. 5/4 is 1 1/4. That's just positive 1.25, exactly. If I plug in negative 2, I get negative 4 plus 1 is negative 3 over negative 2 minus 1 is negative 3. That's plus 1, exactly. If I plug in negative 1 into this function, I get negative 2 plus 1 is negative 1 over Negative 1 minus 1 is negative 2. Looks like I get positive a half. So I could go ahead and just plot these points. Negative 3, 1.25. Negative 3, 1.25 is going to be there on my scale. Negative 2, 1. Negative 1, 1/2 is right here. So I'm starting to see some points line up, right? Let's go for some positive values now. When x is equal to 1, if I plug 1 into this function, the denominator is 0, right? Like if I try to plug in 1, I get 3 over 0, but of course that's undefined. 1 is the one value of x that's not in the domain of this function. If I plug 2 into the function expression, 2 times 2 is 4 plus 1 is 5 over 2 minus 1 is 1, so I get 5. If I plug in 3, 2 times 3 is 6 plus 1 is 7 over 3 minus 1 is 2. 7/2 is 3.5. If I plug in 4, 2 times 4 is 8 plus 1 is 9. 4 minus 1 is 3. That's 3 exactly. If I plug in 5, 2 times 5 is 10 plus 1 is 11. So that's the numerator calculation. 5 minus 1 is 4. So 11/4 is 2, let's see, 2.75. So let's add these points to what I have so far. I have 2, 1, 2, 3, 4, 2, 5. I have 3, 3.5, 3.5 is there. I have 4, 3. I have 5, 2.75, 5, 2.5 is there, so 2.75 is there. And that's what I got so far. And I mean, I think we can kind of see we're curving around here, and we're curving a bit around here. I'm kind of curious about, what's happening when x gets very, very large here, right? It certainly doesn't seem like the x-axis is a horizontal asymptote to me, like it was for 1 over x. Let's see what might be going on here. And so what I'm going to do is I'm going to calculate a few more positive values. 6, 7 I might plug in for x. 2 times 6 is 12 plus 1 is 13 over 6 minus 1 is 5. 13/5 I think is 2.6. If I plug in 7, I get 2 times 7, 14 plus 1 is 15 over 6. 15/6 is 2.5 exactly, right? If I plug in 8 into the function, I'm going to get 17/7, which is about 2.4. So let's see, 6, 2.6, 7, 2.5, 8, 2.4. We're going down a little bit. Now it looks like we're kind of starting to level off. What I would do is, I'm going to jump down the line a little bit, right? 10, if we plug in 10, we get 21/9, which is about 2.33. Now I'm going to jump way down the line. I'm going to look at what happens when we plug 100 into this function. So I get 2 times 100 plus 1 over 100 minus 1, right, into our function. That's 201 over 99, which is about 2.03 when I check on my calculator. If I plug in 1,000, I get 2,001 over 1,000 minus 1 is 999. That's about 2.003. So what I'm seeing is I'm getting really close to 2, right? And on my graph, y equals 2 is right here. If I go to the right, I'm putting in sort of a dotted line here, because what it seems that I'm getting closer and closer to that y equals 2 value, and it also seems like I'm not going to pass below, because I put in 1,000 and I was still a little bit bigger than 2, right? Okay, so we got an idea of the graph there. What about when x is very negative? And I'm just gonna, I think I'm gonna just jump down to negative 10 and a negative 100. When x is negative 10, I get negative 19 over negative 11. Now a negative divided by a negative is positive. That's about 1.73. At negative 100, I get negative 199 over negative 101. That's about 1.97. At negative 1,000, I'm going to get negative 1999 over negative 1,001. Okay, positive. That's about 1.997. So what we're seeing there is this 1.99 business. We're, again, very close to 2 as we move to the left, but we're slightly below 2, right? So this line, y equals 2, which is a horizontal line on our graph, is a, I'm going to say the line y equals 2 is a horizontal asymptote. So we can see that as x approaches infinity, f of x, the y values approach 2, the y value of 2. And we can also see at the other end, as x approaches minus infinity, f of x approaches 2. Again, those are y values at 2. That's our end behavior at each end. Now we got to look closer in the middle, closer to what's going on around this undefined value of x right here, where x is equal to 1. And so I'm going to look at just x equals 0.5, 0.9, 1. We already know the function's undefined. And then at 1.1 and 1.5, and plug in these values. Now I get 2 times 1.5 plus 1 over 1.5 minus 1, right? When I plug into the function, that's exactly equal to 8. At 1.1, I get 2 times 1.1 plus 1 over 1.1 minus 1. I just want you to see that you could do these calculations by hand. I get 3.2 over 0.1, that's 32 exactly. Whoa, wait a minute here. So at 1.5, we have, at 1.5, we have the y coordinate 8. 1.5, we're at 8. So this graph starts shooting upward, and at 1.1, we're way the heck up there. So I'm going to draw a dotted line coming up here, because my graph is getting closer and closer to that vertical line, right? And when, let's see, at 0.9, when I plug in, I'm just going to tell you what I get. I get negative 28. At 0.5, when I plug in, I get negative 4. I did that calculation ahead of time. So 0.5, negative 4 down here. Looks like our graph is plunging down. At 0.9, very, very close to when I'm way the heck down there. So I can see that I keep moving closer to that vertical line, and I don't cross it. Right here, the line, we call that vertical line x equals 1, because a vertical line has an equation of the form x equals a constant, just like a horizontal line has an equation of the form y equals a constant. So the line x equals 1 is a vertical asymptote. So what we want to be able to do, we want to be able to identify these asymptotes quickly, right, without having to plot zillions of points. And that's what we're going to talk about next. Now, just before I finish this up, I want to add a little bit more notation here. We say that as x approaches 1, that's where the vertical asymptote is, from the right, there's that little plus sign, f of x, the function values, shoot off to infinity. That means y values go off to infinity. And likewise, down below here, we would say as x approaches 1 from the left, now that doesn't really mean negative numbers. It includes negatives, but it also means numbers like 0.9, 0.5. It just means numbers that are a little bit less than 1, a little bit to the left of 1. F of x approaches minus infinity, again referring to y values here. So that's the abstract notation for the end behavior. And I think we got our graph here. We got these two asymptotes. It's a shape very similar to f of x equals 1 over x, but the asymptotes have moved around. So I don't quite have it all in there at once. Let's maybe just zoom out a bit to get a wider picture here of more of the graph, sorry. And so we'll start talking about our general procedure now for just being able to quickly find the asymptotes, mark the asymptotes, and then sketch our graph with very little bit of point plotting. That's what comes next.